Alrighty, are we live? Hello, welcome. Hello, hello. Here with another problem to work on. Howdy. I guess we'll get right into it. I don't know. Just praise God. It's a Sunday. Thank God for Sunday. Thank God for everything. I'm so grateful. Let's just get into it, man. Let's just get into it. I have all kinds of things to think about and work on and whatnot, but I can think about and work on those things later. Let's take a look at this problem now. So sequence reconstruction. Let's see. Hopefully my volume is high enough. Yeah, I think so. I raised it a little bit. I've been kind of speaking lower lately, especially I'm feeling a little bit sick. So check whether the it's got a lot of downvotes. Ooh. Check whether the original sequence ORG can be uniquely reconstructed from the sequences in SEQs, S6. Org original sequence is a permutation of the integers from 1 to n, with 1 less than or equal to n. N is less than between 1 and 10,000 inclusive, right? 10,000 inclusive. Reconstruction means building a shortest common supersequence. Excuse me, what? A shortest common supersequence of the sequences? That's an unusual construct in sequences. A shortest sequence so that all sequences and seeks are subsequences of it. Okay, I think I understand. Determine whether there is only one sequence that can be reconstructed from sequences, and it is the original sequence. Oh boy, okay, it's a doozy. I can see why I got a lot of downvotes. I think problems that are hard to understand, as written, I think people don't like. There may also be like some edge cases and things with this that are kind of tricky. People don't like to fail. Neither do I. And I got updated. Maybe it got updated because of the downvotes. Has been changed to a list of strings instead of a 2D array of strings. Please reload the code definition of the list changes. Okay, fair enough. Vector of vectors, list of list. I gotta sneeze. Yeah, my body's struggling. I've been really stressed and having a hard time sleeping and whatnot. Just I don't know, man. I have a lot of it's my own doing too. That's the thing. It's like what do you call that? I've been doing things to make my life more difficult than it needs to be, and stressing me out. It's my own fault. That's the worst when you know it's your own fault. That's when it's like, whoops. Check whether the original sequence org can be uniquely. I'll just look at some examples. That might be easier. 1, 2, 3, false. 1, 2, 1, 3. 1, 2 is not the only sequence that can be reconstructed because 1, 3, 2 is also a valid sequence that can be reconstructed. Okay, I guess the numbers are. I'm not sure I fully understand. 1, 2, 3, 1, 2, false. Can only be 1, 2. I guess you can select numbers from the sequence too. If that makes sense. So you can do 1, 2, 3, or you can do 1, 3, 2. I guess you can't select the same number twice though. So once you've selected a number, you can't use it again. Okay, 1, 2, 3, 1, 2, 3, 1, 2. Can't use this 2, 3. Okay, I think I get it. 1, 2, 1, 3, and 2, 3 can be uniquely reconstruct the original sequence 1, 2, 3. 4, 1, 5, 2, 6, 3. 4, 5, 2, 6, 3. 4, 1, 5, 2. So you do 4, 1, 5, 2, 2, 6, 6, 3. So I guess this is like really simple in some sense, is that you just you basically can only select one element at a time, and is that right? Like apparently you can't do 2, 1, 3. though, right? Like, wouldn't that make this false? So it's like super confusing, right? The definition. Right, like why can't you go 2, 1, 3? Why wouldn't 2, 1, 3 be impossible for this? Because apparently you could do 1, 2, 3 here. You can do 1, 1, 3, 2 here. So this one you could do 1, 3, 2, but you can't do 1, 3, 2 here. Why is that? 1, 1, 3, 2. Permutation of these integers means building a shortest common subsequence of the sequences. Subsequence of the sequences in SEQS. All sequences in SEQS are subsequences of it. I'm so confused. Common supersequence. So these are all subsequences of 1, 2, 3. That makes sense. But 1, 3, 2. I think I get it. 1, 3, 2. You can get 1, 2. You can get 1, 3. But 3 would come before 2. So 3, 2. So this isn't a subsequence of. Okay, I think I understand. So you're given a set of subsequences. I could see why this would frustrate a lot of people. It's actually a really interesting question. I like this question. Just like the attempt itself, I have to respect it. Not that I have to, but I respect it. So what they're saying is, if these are all subsequences of a particular sequence, is there only one such sequence that satisfies that condition? Is it unique? That's the first thing. And the second thing is there any sequence that satisfies that property, that these are all subsequences of that? So, for instance, 1, 2, 3, and further. So, does there exist this sequence where all these other sequences are a subsequence of it? Is it equal? Is there only one that exists? Is it unique? And finally, is it exactly equal to this original suggestion? So they suggest a supersequence. So really, I mean, it's kind of easy because you can just say, well, are all of these subsequences of this original? That checks immediately, like, that gets rid of a whole lot of possibilities immediately. The only thing you really have to check after that is, so if that's false, you're done, right? You terminate early. And that should be relatively easy to check. However, and these are although maybe it's not that easy. I mean, these are subsequences, which is not the same thing as a subset. So that's kind of interesting too. The other thing to consider though is it possible that there's another sequence that you can take the subsequence of that sequence, and these would be these, or is there another sequence that exists where these could be the subsequence of that? That's a little trickier. That's a little bit harder. That might actually be, I think, more difficult, and probably the thing you would want to check first. That is challenging. I'm actually not sure how you might do that. Yeah, how would you show, right, it's false if there's more than one of these sequences. Yeah, that's a little bit harder. That's quite a bit harder. Sequences, 32-bit signed integer. Length is between 1 and 100,000 inclusive. Work as a permutation, and these numbers are between 1 and 10,000. Really interesting question. I like this question a lot, but just like the novelty of it. But it's definitely a challenging question. Definitely hard. Not hard, but challenging. I think that the trickiest, the thing I'm not sure how I would do is the finding out whether this is uniquely defined. the super sequence, or the supposed super sequence. Also, I don't really know how efficiently I could check that each of these sequences are a subsequence of the original. Because I think the problem with that is, I don't think that's I want to say I don't think I want to say it's a very optimal way to check that. Like how big or how many sequences do you have? You have 100,000 of them. Yeah. So if every 100,000 of them takes linear time, that's a billion operations. So that's way too many. Like I don't necessarily think I could check this in constant time. Each sequence is a subsequence. It might actually be easier to create a hash set of the possible super sequences, and then, but even that, like there could be a lot. Well, if there's even more than one, then you're done, right? So it really shouldn't be that hard. Actually, it should be, but still, let me see something here. The shortest subsequence, so that's really challenging too. That's really challenging, actually. It's really like, because there could be a few different things that give you the subsequence. Also, I think the order matters. See, that's the thing. Yeah, the order matters. I think because, yeah, 5263 is a subsequence. 4 and 52 is a subsequence. Are they contiguous? They're not contiguous subsequences. They're just subsequences. Really interesting question. I gotta sit and think about this for a while. Let me lay down and ponder it because I don't have an immediate solution. And I think if I got this in an interview, I would get owned. I think that would be it. Yeah, it's not a problem I'd be able to solve quickly. Definitely not. Especially the time bounds on this are pretty low. Let me put my headset down. I'm just gonna ponder it. pondering some things here, and it's interesting. Carefully re-examining some value n. Org is a permutation, which means that this permutation, there's only one of each element, which is significant. The sequence's length, and the number of them could be 100,000 of them. And you say each number is, excuse me, fits in a 32-bit integer. Well, I mean, that kind of goes without saying, right? Because of where n, the value of n, and this. Obviously, well, does it go without saying? Original sequence, building shortest common subsequence. Determine where there is only one sequence. Well, yeah, I mean, if this number exceeds, whatever n is, the largest value of n from the original, which is the length of the original, right? The original is, and so if any of these numbers exceed that original length, then automatically it's false. So I guess in theory you could put whatever numbers you want, but that also puts a bound on what these sequences could be. So they'll have to be as small as the, or at most the size of the original, in terms of their individual lengths. So oh no, wait. Oh, they're missing something. They're not saying how many sequences are there. They're saying the length of each sequence is between 1 and 100,000. It's not saying how many sequences there are. They're missing how many sequences there are to look at, which I'm assuming aren't that many. Hopefully there aren't that many. I don't know. Could be a lot though, I guess. But either way, I think we would need to do this efficiently. So what's interesting is basically what I'm looking at or thinking about is that these sequences, they basically define an order, a new order on the numbers in terms of which one comes before the other. And here you say 1 comes before 2, 1 comes before 3, which implies, but it doesn't make a comment on whether or not 2 comes before 3 or 3 comes before 2. So really the question is asking, do these sequences define a total order on the set, on the original set? If they don't define a total order, in other words, it's ambiguous whether 2 comes before 3 or 3 comes before 2, then we return false, right? We don't actually know what that relationship is. Part of the problem with this approach, though, is that this is at least quadratic times complexity with respect to n, because we're checking basically, excuse me, every number against each other in their comparisons, relative comparisons, which you don't necessarily need to do that or want to do that. The other thing that can happen is it's not a total order, but a total order is incorrect or false. So you could have like 6, 1 and 1, 6, or 1, 2 and 2, 1 are the two subsequences, but that would mean that 2 comes before 1 and 1 comes before 2, which is the contradiction. So I guess in our total order, we're also showing that none of these elements are going to be equal to each other as well. It's sort of a given in our new ordering. So that also won't work. That's a situation where no order exists at all. So we want to show that there's one total order that can be defined by these sequences, and that one total order is exactly the original that they gave us. So really you just need to check, is 1 less than 2? That's present in one of these sequences. Is 2 less than 3? That's not present in any of the sequences. and then you do 3 less than 4, etc. So in order to show that, yeah, I think that's really all you need to check. You just check 1 less than 2, 2 less than 3, etc. And then you also would want to check that the opposite is not true. That you don't see, you see 1 less than 2, 2 less than 3, but you don't see 2 less than 1 and or 3 less than 2. And then you also do need to see, yeah, if you don't even see that element at all in any of the sequences that you're looking at or looking for, excuse me, then you're also not then you're also not then you're also going to return false. I guess what you do is you just put all of these into a all the ones you're looking for into a set. Excuse me, and just loop through the sequences one by one to try to find those. Something like that, I guess. So you'd have 1 less than 2, but then also 1 less than 3. You don't really need 1 less than 3 though. I don't know. It's kind of hard to say. Like, storing all this information. You don't necessarily care that 1 is less than 3. Should you even store that? Probably not. I think what you do is I don't know. I'm struggling to kind of figure out what to do. Part of me thinks you could like make a graph, but again, this kind of makes like a total graph, which you really don't need all that information, and that's actually kind of expensive. That's a lot more edges than you need. There are way more edges there than you need. Excuse me. Strongly considering rewriting this as a graph problem. I think that's okay, actually. Like I said, it's kind of a lot of information, though, to go through all these sequences, all the edges. Right, each sequence could be 100,000. We want to use directed edges, I guess. Not undirected edges, but directed edges. And if there's a loop, you know, one edge pointing back to another, then obviously that's wrong. So we have an edge from 5 to 2, from 2 to 6, 6 to 3, 4 to 1, 1 to 5, 5 to 2. I say, okay, we get 4 to 1, we get 1 to 5, we get 5 to 2, we get 2 to 6. we get 6 to 3. Problem with this though might be that so 1 2 1 3 and 2 3, so you can do 1 2 3. We don't have an edge from 2 to 3. The problem with this approach, this idea is, well, it's actually it's not more processing than we could possibly do, right? Because we do need to look at every element in the sequence, so that's actually probably optimal. It's probably an optimal approach if it's correct, but whether or not it's correct is another question. Excuse me. So whether or not it's correct is another question because of because you may find yourself in a situation where first off, detecting those backward edges is not so obvious, right? The cycles. That's the first thing. Detecting the cycles is not so obvious. The other one is detecting the cycles is not so obvious. I think it's a little more obvious if there's ambiguity, so you don't actually have a connection from one to another that you need. That's a little more clear. That's fine, that's handled. I want to say something like if you had 5 6 3 here, like you have this 1 5 4 1 5 2, right? You could do 1 5 6 3 or just 5 6 3, right here, and 4 1 5 2. You have this 5 6, but you still would have this 6 3. Like that's fine. That's kosher. It still works. Yeah. Excuse me. I think what you can do is just to make sure there aren't cycles, just when you're walking through it, create like the visited set, and if there are any edges that point back to the visited set, then you have a cycle. I think just do it that way, and then you have a problem. I think that handles everything. I think that's it. I think that's all you need. Excuse me. Yeah. You also when you're walking through it, you just make sure that every node is represented. Because if the other question is like, well, what's the shortest size set? It's like, well, every node that's present in the sequences has to be present in the set. So that would be that is the shortest. It's just that one, and they're more or less unique, the numbers. Like I said, if you see more than one number twice, then immediately you should have a contradiction. Yeah. That should, if you see a number twice, that means you're going to see a contradiction in the order. So I think I got an idea. I think I got it. Let's see how we do. So we'll include unordered set. This will be the visited set. Clearly we need vectors. Now the question is, do we need, how are we going to store our we can store our graph by a vector of vectors, I think. I think it's better to do a vector of sets, of unordered sets. So it's easy to check and figure it. We just need to do a neighbor check, basically. A vector of unordered sets. Because we have n, we know how big we need to make our graph, so to speak. Yeah, so we should be able to do that. Let's see. We're not going to modify any of these. Okay. So build graph, directed graph from the set of sequences. We'll just say G. It's going to be original.size plus 1. And the reason why we're going to do plus 1 is that this is 1 indexed. So we're going to also keep our graph 1 indexed. It's a little bit more memory than we need, but it's a little easier to think about, I think. And we're just going to have an unordered set. Initialize unordered set of integers for const auto reference of, let's call it S sequences. We're going to say for, we'll do int I equals 0, I is less than s dot size minus 1, plus I. Let's say int A is equal to s of I, int B or B is equal to s of I plus 1. All right. There is a tricky thing here also. Yeah, this is like a very subtle thing. We're actually going to do this in tandem. Well, we can do it in 2 different loops. So we'll do 2 loops. All of the values present in the I'm sure all the values present in the input sequences are accounted for. Terminate early. If not. So basically, we just check to see that if org.size right? So it might be size n is less than or equal to s of I So if org.size is less than x, right? So if there's 9 elements, it's 1 through 9. If this is too small, then we return false. Otherwise, if this check passes, that means that all of the elements are going to be found. Every element that shows up in any of the sequences is going to show up in the original sequence. The reason we do this is that, like, you have a situation where you throw like a 4 in, you have this, something that returns true, 1 2 1 3 2 3, and there could just be a 4 sitting out excuse me, a 4 just sitting out by its lonesome, which means that there has to be a 4 in the original. If there's no 4 in the original, then we have to return false. And it could have it won't get touched by this sequence because this is checking. At least there has to be at least 2 elements to consider. So you'd want to perform this check. This also kind of verifies that like you don't have like a random number that is just way out of bounds. Also, it kind of does 2 things at the same time. Yeah, it verifies that every number is there, and then also that the numbers that, yeah, actually just verifies that every number is there. That's really it. Yeah, just do that. Yeah, which this check isn't really going to do that. So build the neighbor set according to given sequence, or expound set, the neighbor set according to the given set. So we would say, so G of A insert B. I think that's it, actually. I think it's that simple. Yep, that's it. Traverse the graph, the built graph, using the original sequence. We cannot visit every node in the sequence in a given order according neighbor graph and return false if we see any neighbors apply a loop cycle in the graph, then we must also false an impossible supersequence. So we would say I equals 0, I less than original dot size minus 1, increment I, we'll say int a equals original of I, b equals original of I plus 1, and we're going to say so is it? I'm going to say if okay, if G of A dot count of B is less than 1, return false. Okay. For true. Neighbor in G of A. For each neighbor in G of A, if visited dot count neighbor excuse me is greater than 1, and return false. Okay, so yeah, we're going to check all the neighbors, and see if it's in our visited set. You can actually do the intersection. It's probably better. That should be logarithmic time to count to get the intersection. I'm actually not sure. There could be a lot of neighbors for this particular number. It could be a linear number of neighbors. This could actually make this very slow, this part of the program. This might be too slow. How can we check that? Excuse me. We could actually do this here, I think. Whilst doing so, sure that no aren't any no, that's not really that's really awkward. That's very awkward. Oh no. It could be a lot of neighbors for a particular node. Oh no. There could be a lot of neighbors for a particular node. And somehow one of these goes back the other direction, the other way. Creates a contradiction. How could we check that? Well, you don't want to loop through all the neighbors each time. That's really a lot. You don't want to go the other way around either, where you check all of the visited nodes. Oh, this is super awkward. Oh no. I'm really done again. Excuse me, I thought I had an idea, but this might be way too inefficient. No. 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 Oh, okay. Alright. Alrighty. How do we do this then? What do we do? How do we do this and what do we do? That's a good question. That is a good question indeed. What do we do? What do we do? Hum. Indubitably, indubitably. Indeed, indeed. My thinking was that, well, you could check if any of the neighbors of this set, of the value you're looking at each point, any of those neighbors are any of the elements you've already seen. And while that would be correct, it's not very efficient. It's kind of the issue. Alternatively, what you could do is build a that's not really good either. I don't really know. I guess my thinking is when you're building your neighbor set in the first place, you could check to see if there is something backwards already, if there's a cycle. But the problem isn't so much that the issue is that doesn't actually tell you if there's a cycle, because it's an issue of transitivity, right? In other words, you can go A to B to C, and if C has something pointing back to A, then you have an issue. Excuse me. However, A to B to C, and then if C points back to A, you have a problem. However, excuse me, however, C pointing to A doesn't necessarily imply that we don't necessarily know that like following A to B to C means that A has a path to C. But unless we update in our neighbor graph every spot, all the different sort of transitive parts, directed edges, then yeah, which we don't necessarily do that. I guess that's my point. Oh no. Oh no. Huh. Yeah. Huh. The reason why we don't update that is because it's quadratic, right? Because that gives us quadratic runtime, which is expensive. It's too much. We know that'll fail in the larger test cases. If we could do n log n time, that's fine, but even that is expensive, or not expensive, challenging, because there's not an easy way to check the set difference between the set difference between the oh, excuse me. Actually, wait a minute. Wait a second. Actually, the set difference might be okay. Oh, no, I think you could do the set difference in logarithmic. If you could do the set difference in logarithmic time, then we're in good shape. Because we're just looking for the neighbor set, and the difference between the intersection of the neighbor set and the set of things that we've already visited. Actually, I think if we store these things in sets rather than in unordered sets, I think we could take that difference. I don't actually know how to do if we could do the difference between unordered, if we do an unordered set difference, and how much time that would take, or intersection. Actually, this may not be a problem. Let's see. Maybe I'm wrong here. Excuse me. Maybe I'm not wrong here. So we're doing kind of poorly on time. Yeah, over an hour. I kind of expect that. I mean, this is like a pretty novel question. Kind of unfamiliar to me. What is the runtime? Comparisons. Yeah, a lot of it's linear time. That's a little bit too expensive for me. Excuse me. Oh man. Wow. Sorry. Yeah, I'm definitely sick. I don't know what I'm sick with, but definitely sick. Not ideal. Not the best. Isn't there a way to... Got a lot of downvotes. Yeah, kind of struggling because I thought you could do this in logarithmic time. Trying to do it in linear time. Oh, sorry, logarithmic time. Trying to do it in logarithmic time. I thought you could do it in logarithmic time. If you do it in destructively. Also, someone's dog sounds like they're having a hard time. I don't know what's going on. I don't know if I should intervene or do anything. I thought I read something about set manipulation. Hold on, am I crazy? I thought I found something on Wiki. There's a way to do this. There's binary search tree intersections. Nope. No. I thought that I saw something the other day. Excuse me. Yeah, there you go. Union, intersection, and set difference on an AVL tree. So the union, okay. M log n. Okay, got it. Never mind. Alright. Never mind. I was gonna say, I was like, I thought. No. So they're. Never mind. Alright, I thought maybe I can get away with the faster, do a set difference somewhere here, but that's not gonna work. No, we need, yeah, we need something faster, something better to find the cycles in this tree. I mean, okay. No. No. Yeah. Uh, yeah, the problem. Well, maybe this isn't so hard. I mean, I guess maybe I should just check directly if there are any cycles. Maybe that algorithm's not too bad. Because that algorithm should be fairly quick, right? It should be, you say for each node, from the starting point, excuse me, yeah, really it would be any cycle at all in our graph should cause a problem. Because what can happen, so it should be relatively quick to determine that if we have a cycle, relatively efficient, because there's only O of n node. It should be take O of n time, where O of n is the number of nodes after we built the graph. And the reason is that we just take each node, right, and we say, okay, give me all the neighbors, recurse on each of those nodes. We're going to add each node that we're going to look at, add that to the visited set, and then each of those nodes, those have neighbors, right? And we would add all of those neighbors. So if any of the neighbors, actually, hold on, I gotta think about that too now. It's so tricky. My thinking, I don't even know. Well, my thinking is that we're going to add all these nodes as neighbors. We're only going to visit each node once, and so even when we sort of populate this neighbor set, as soon as we see a node that we've already visited again, that would imply that we have a cycle and we stop right there, right? So we're never going to do more than, if you sum up all of the edges that we check, we're never going to do more than O of n, because as soon as we do one more than O of n, we actually terminate early, right? So there's sort of a pigeonhole principle bound there. But the problem with that is you could add, like, if you have the first node has like 5 neighbors, I think once you process one of these nodes, like the order, that doesn't necessarily give you the order, because, excuse me, that doesn't necessarily give you the right order, because you could do like, those nodes could point to each other, but not necessarily create a cycle, because this is directed. So even though, yeah, so that's not quite what we're looking for, but it's very close. I want to say, like, it's okay for those nodes within that set to point to each other, but it would not be okay. Well, yeah, actually, no, that's that's fine. The issue is if you point, quote unquote, point backwards, which is kind of hard to tell if you take all of the values at once, I guess. So maybe you do need to just go one at a time. Yeah, that's really awkward. That is really awkward. Excuse me. Sorry. Is there maybe a breadth first traversal we can do where, maybe we do it the other way, where actually I don't know. How, how do we do this more efficiently? Um, yeah, a round robin is not efficient enough. Nope. Shoot. No. You know what you could do? You could do something like assign each number an index, right? And then you're checking if any of the neighbors have an index that's smaller than the current number. So, yeah, that could give you, well, that's actually probably the thing to do. So, oh, yeah, there you go. Let me think about that for a second. Excuse me. Yeah, that's kind of what we want to do, I think. Translate each number to an index, and then compare those indices. See if any of the neighbors have a smaller index. And you can actually do that when you, while you're building the neighbor graph. Or more or less building the neighbor graph. I think part of the reason, right? Part of the reason why it would be inefficient to I actually don't know if what I was suggesting before about visiting every neighbor, if that even really matters in terms of the time complexity, because it looks like we're visiting every neighbor anyway. Like we're going down every one of those paths anyway, because we're building them into the graph in the first place. So it really shouldn't matter. Well, I think the reason it makes a difference is, well, no, it shouldn't, no. Because that visited set was just, it's a constant time check. Nope, shouldn't make a difference. So I think the idea that I had in the first place was fine. Maybe, unless the idea to like create a, the graph in the first place is wrong, but I don't think even that's, excuse me, I don't think it's even possible to avoid that. Yeah. Huh. Yeah, because you have to visit every element to know what you're working with. Yeah, I guess maybe there is one issue with this problem that I would complain about, is that I would want to know the constraint size down here. Over here, this one more constraint on how many of these sequences are we going to get, these subsequences. Excuse me, burping into the microphone. Yeah. Excuse me. So actually, I think this is it. And really, it's just, yeah, it's at least one. I think this is it. It's really all you need. So we got 4 examples, right? Let's give it a shot. See how we do. So coding this is pretty quick, but figuring it out is definitely a challenge. Took me quite a bit longer than 20 minutes, 15 minutes. 5 minutes, 7 minutes to figure it out, and 7.5 minutes to figure it out, and 7.5 minutes to program it. I don't think so. Not on this one. On this one, it took me like an hour to figure it out, and then a few minutes to code it. I think I got it though. Yeah. We just go for it. I think so. I think we just go for it. Yeah. Yeah. Okay. Oh no, really? Come on, man. I thought I handled that edge case too. I was like, what about the degenerate cases? I thought I got them. Oh, I'm so sad now. Really? I thought I had it. Wait a second. So this one is wrong. What is the one in the empty set? And what is this supposed to give us? False. 1 in the empty set. So, oh, I see. So I only checked if our sequences have too many elements, but if the original actually has more elements than the target set. Oh boy, I didn't really check that. Yeah, I didn't really check that, huh? All right. Yep. Uh-huh. Sure. Sure. The original sequence. Minimal. I'm gonna put that in quotes. The way we check that is we have this target. If not, or less than or equal to 0, then add x. Excuse me. Building a target sequence. Oh man, oh man, I don't know. I don't even know what to say. I think so here we return false now. Okay, 1, I'm upset that I got that wrong. 2, I'm upset that I missed that part. 3, what excuse do I have to have, although I'm upset, what did I do wrong? How come that happened? How could I have avoided that? I don't necessarily, I think I need to be more careful to avoid that, if I wanted to avoid that. How could I have been more careful? Think a little bit more about making sure this is minimal. Although in general, I think it's just experience. Because I just didn't think, I mean, the quote-unquote the degenerate cases. I could have just run the degenerate test cases to see what happens. That would have been good. I would have got some wrong answers. Running more test cases is generally pretty good. But yeah, for what if this is empty and empty? I mean, we could still do that, right? We could do empty, empty. We could do empty, 1. I think all of those will get the right answers. Invalid test case. Okay. So that's a test case that we can't do. Actually, that's also incorrect. Let's see. Excuse me. Oh. Let's see, how do we do here on these different tests? Alright, let's go for it. Oh man. course. Now, I think this may not be my fault, this one. I was not even aware that these sequences could have duplicates in them. Nowhere was that indicated. That's awkward. What is that supposed to be? Expected false. True. Um, 1, 1. Yeah. There couldn't be duplicates, right? But I thought I handled that case. I guess I didn't handle. There's one part of this I didn't handle, which is um, yeah. Uh, or if it's pointing back to itself. um, Neighbor equals A, basically. Wait, really? Um, what? True. Wait, why do we get true on that one? One more time. Oh, we don't. Oh, we didn't add anything to the visited set yet. Oh no. Oh no. I did actually handle this. Oh no, I did handle this case. I just forgot to add it. Excuse me. Oh no. Uh-oh. Uh-oh. Oh wait, this still is giving us the wrong. What? I'm so confused. So we visit 1. We go to 2. Oh. Didn't check that one either. Check for loops on the last as well. Yeah. Um, G of org last. Yeah. Oh, hold on. Okay, so we got false on the last one, but this one shouldn't be correct either. And we could do either of these. It really should be both of these. Neighbor equals A, and also neighbor equals A, which is worked out back. There we go. Oh no. I'm afraid to hit the button again. It's definitely going to be some. Excuse me. I can't believe I got this wrong. I mean, I believe it. It's not surprising, but it's upsetting. It's frustrating. It's like, man, I'm afraid I'm going to run out of time as well. Oh, we got the test cases. Can we do like 1, 2, 3, 4, 5, 6, and then we have, 1, 2, 3, 2, 3, 4, 3, 4, 5, and then 5, 6, or just 1, 6. Afraid my approach isn't even correct. That would be upsetting. And 6, 1. How about that one? Let's try that. Okay, still right. Somehow we got that one right. I don't know how we got that right. 1, 2, 3, 2, 3, 4, 3, 4, 5, 1, 6. Wait, what? False for the last two? The bottom one I understand is false, but how come this one's not false? How come this one's not true? It's 1, 6. 1, 6 is a subsequence. 1, 2, 3 is a subsequence. 2, 3, 4 is a subsequence. 3, 4, 5 is excuse me, a subsequence. I guess because 6 could go anywhere, right? 6 could go 1, 3, 4, 6, 5. We don't actually have anything to 6 except, yeah, we don't have something from 5 to 6. So it can go 4 to 6 or 3 to 6. It's not unambiguous. I think that's why. Yeah, the ambiguity. Oh yeah, not that I can't believe it, but I did cover that case. I thought I did. I'd known that I'd done that. But now this will also be false because now it is ambiguous. This one's not ambiguous. Pretty interesting. It's different cases. So the last one will be true, but the bottom one above that will be false. So then we will have a excuse me, that loop back. Oh no, it's true and true. Wait, what? No, 1, 6 is okay. 5, 6. It has to go. We have to go from 5 to 6. 1 to 6 is fine. If we have 6 to 1, then we have an issue. All right, I probably missed some test case somewhere. Oh no, we got it. Okay. All right. Took an hour and a half. We got destroyed. Dude, I got owned. I got absolutely destroyed. I was right though. I mean, I had the right idea. Yeah, had the right idea. Got it. It's just that was really hard, I guess, to kind of go through all of that, get it just right. I can't believe I got it wrong too, twice. I mean, the idea was there. The idea was correct. I kind of misprogrammed this part. I forgot to add the visited set, and I also didn't consider loops with it to itself, which I should have. And I also didn't include 3 things I missed: loops themselves, actually coding it correctly with the visited set, and then finally checking the last element for the cycle as well, because this is a sort of a double. The way that this loop works, it kind of jumps, excuse me, jumps sort of 2 at a time. Yeah. And so we end up missing. I really should have made a separate loop for this part, I think. Yeah, I actually should do it as a separate loop entirely. I think this is incorrect. So we'll get rid of this and get rid of this, and then say I have this visited set. Then we have org of I. And this could just be const auto or constant A in org, right? And then we do this, perform this check. Oh, yeah, as we're visiting. All right, this tells us whether or not we can actually make it across, make all those hops to where we want to go, and then unambiguously, and then this tells us whether or not we'll have any loops while we're making that journey. Yeah, and we'll also, and then we don't need to check the cycles there. All right, then we do that. Sure, no cycles. and that'll include the last element as well. Yes, that's still correct. Yeah, that's actually how I should have coded this. Make that a lot clearer and simpler. I mean, this is pretty straightforward. This is just build the graph and go from there. A few different pieces to it. Unambiguously define the sequence, make sure there aren't any cycles, make sure that we're minimal, right, by gathering all the targets, comparing that to the size, right, because you can have a sequence that has too many numbers that we don't need that many numbers, and vice versa. Make sure all the targets are less than the size as we do that, and then can actually probably cut this part out now and just go the other way around. Well, no, this is better. No, we do want to do this. I take that back. No, that's fine. Yeah, I'll dump everything into a target set if we don't already. This, by the way, this is idempotent, so you don't really need this check. Should be fine. You also don't need this A and B here, but I kind of prefer to specify. Yeah, I mean, the code is actually really simple once kind of discerned, and once you program it, it's really not that bad. It's just, it may not be the most efficient, certainly not, but I don't actually know how to do this better. I hardly even know how to do this at all. I wasn't even confident I would get this correct. I think this is reasonable. You can code this up relatively quickly. If you could figure it out in a short period of time, you could code this up in a few minutes. This really isn't that bad at all. It definitely was challenging though. Like, I struggled. Yeah, we're almost at over an hour and a half now on this. Kind of mulling it over, thinking about it, looking at the different pieces. Really, definitely. Excuse me. Definitely a challenging question. Definitely a challenging problem. An interesting problem, challenging problem. I'm grateful for it. Got a little more experience. Kind of subtle things that I missed, but I think I got the right idea, the general idea. That was pretty hard, I think, overall. Like, that was pretty tough. I don't think I'd be able to do that in a 45-minute setting without having seen like at least 4 or 5 questions that are of similar nature and having solved them already. So yeah, definitely need more practice. Pretty good. Pretty good. Sweet. Alright, I'll end it there. Thank you for watching. I'm gonna go take a break for a while. I think I'm gonna go get food, I suppose. I don't know what I'm gonna do, but just take a break. So yeah, talk to you soon. Take care. If you like this kind of stuff, don't forget to subscribe.